Good day, class. So we will now discuss the second to the last topic in process controls, and that is closed loop transfer functions. Now this was discussed already inside the classroom, but for some technical issues I was not able to have it record in a manner in which you can readily understand because of some connectivity issues. Now, let's start off this particular topic with the standard block diagram symbols, the representations that you will be seeing in our block diagram for a system consisting of a stirred tank heater. Now, the R there will be representing the set point or the desired value of the temperature for the controlled variable. The C is the controlled variable. The E or the epsilon that you'll be seeing would be representing the error. The B is the variable produced by the measuring element, or that's the actual value of the temperature that is being sent to the controller, or rather that is being compared to the set value and sent to the controller. Now the manipulated variable is in the form of the flow of the heating medium, and that is through our final control element. Your U represents the load or the input variables that will be disturbed, or they are disturbances that will cause our C, our controlled variable, to change. The G sub C is the transfer function of the controller, represented by the subscript C that you are seeing here. The G sub 1 is for the final control element, and for the G sub 2, that's for your process itself. Now, the only transfer function here which is not represented as G is the transfer function of the measuring element. So these are the letters, the symbols that you will be seeing later on in your block diagram. Now, for our standard block diagram for the stirred tank heater, now you could see the three transfer functions here for the controller, the final control element, the process, and that of the sensing instrument. You have the U here, the load or the disturbances. The M is the manipulated variable. The C is your controlled variable. The B is the sensed value coming from the sensing device. And you have the error here, the difference, or how much is the sensed value differ from the set value, which is R. Now, the G sub C, the G sub 1, and the G sub 2 are said to be excuse me, the forward path transfer functions. We have only one transfer function that is on the feedback path, and that is for your sensing instrument. Now, if you will take the product of the transfer functions in the forward path to the only transfer function in the reverse path, or that's the feedback path, we will have what we call as the open loop transfer function, consisting of the product of all four transfer functions. And this particular open loop transfer function actually relates the B, the sensed value that is introduced to the comparator, and then with the error being introduced into the controller, to the set point. So it relates the B to the set point. How is this B comparing to the set point? The one that relates that is this G sub C, G sub 1, and a G sub 2. Now, for the block diagram for a multi-loop, multi-load system, but this is not something that we will be tackling in here, just for your information, would look something like this. And for this particular block diagram, we often call this one as the cascade control. This is often encountered in cascade control. So you have a loop, and within a loop, you have what we call as an inner loop. So this is comparable to what you have then in your programming in computer fundamentals, which is C++, the case of a loop within a loop. We call it a nested loop. In this case, in cascade control, and this happens when you have multiple controls already applied to a system, you have an inner loop and you have an outer loop. In this case now, you have what we call as cascade control. We can make the overall transfer function, or we can derive rather the overall transfer function of this system, setting only one output to be related to one input change, even if we do not know exactly how the manner of controls happen with this inner loop within this outer loop. But we can derive, or you can use the principles that will be discussed here in terms of deriving the overall transfer function of the system, again relating one output to one input variable. I am emphasizing that because, as you could see, you have three inputs, the R, the U sub 1, and the U sub 2. In that case, the other input variables has to be set to constant behavior. That way, you can only relate your C, for example, to a change in the set point. Or if we will have the set point constant and one of the loads here constant, then you can relate your C in terms only of one input variable that is expected to change. So that is in terms of this cascade control. Now, for the overall transfer function of a single loop system, let's say we want a transfer function relating C to R or C to U. This is referred to as the overall transfer function because they apply to the entire system. Even though you have set only one input variable at a time to be related to your output. But that is still, shall we say, the overall transfer function of your system on the assumption that one of your input variables or your disturbance is constant. Now, the response to a change in the set point R obtained when we set U equal to 0, meaning there isn't going to be any changes in the input variable, represents to the solution to the servo problem. And this servo problem actually was defined already in our previous lesson. This is the case wherein it is the set point that is being changed to address the behavior of the controlled variable. That way, our control variable will not deviate as much from the set value that it should exhibit. Then what is being changed here is the set point. In cases wherein the disturbances in the form of loads are all assumed 0. Now, the other one is when the response to a change in load this time is obtained by setting the set point equal to 0. This means that you don't have a set point equal to 0, but rather there aren't any changes in the set point. Whatever is the set point, that should be the value that the controlled variable exhibit, or it should exhibit the value more or less in the range of the set point. And this is most of the time the kind of problem that is being worked out in process control. We want to set the value of the controlled variable, so therefore the set point is not to be changed. So what is going to be changed is, of course, the manipulated variable, so that the effects of the load or the disturbances on the controlled variable is, shall I say, reduced or mitigated. That's regulator control. So set point changes is equal to 0. What is changing here is the load variable. Now, the thing is, how do we determine the transfer function based on one particular input variable in the case of the stirred tank heater when the other one is assumed to have no changes at all over time? So this we will discuss one at a time. So for the overall transfer function for a change in set point, meaning in this case disturbances are 0 or is equal to 0, it is the set point that is going to change. The corresponding transfer function that we're looking into is this one. The C being related to changes in the set point, your controlled variable being related to changes in the set point, now is reflected in this particular transfer function. The G here is the forward loop transfer function, meaning the GC, the G1, and the G2 all multiplied. Now, the 1 plus GH is, of course, 1 plus this one we know as the open loop transfer function. Now, question is, how did this came about? This particular overall transfer function relating C to R. Now, if this is our block diagram, actually the original block diagram for our system, for our steel tank heater, is something like this. Okay, this is the original block diagram. If there won't be any changes in the load, this will be out of the picture. This should be, it's just like this one, sorry. like this one, you take out. It's not present there already. So as a result, if that one is taken out of the picture, the block diagram that will be produced, because it's only R that's going to change, is this. So we can simplify the three transfer functions here for the three elements: controller, final control element, and process, into one transfer function. We're going to lump them into one transfer function. You know how to do that. You just simply multiply the three, and that would be your G here, and you have your H here, and you have your set point here. Anyway, the G is already specified in here. When you have written your block diagram in this particular form, from this, it would be easy to write the transfer function of your system now. This is your output variable, this is your input variable, and these are your transfer functions. So when we write the overall transfer function for this system, take note of this particular pattern. The numerator of that particular transfer function would simply be the transfer function of the forward path, meaning this 3 multiplied GC, G1, and G2, and the denominator will be the sum of 1 plus the open loop transfer function. The open loop transfer function consisting of the product of all transfer functions present in our original system, and this is our original system. Now, when from this original diagram you have simplified in this form, then you can write the corresponding transfer function in this form. Now, it's so easy if it's done graphically. So this is how we do it graphical. Okay? Now, you have G over 1 plus GH because this is your transfer function. Your input is said to be working on this to bring about the output. Okay? That's how it's done graphically. But if you want it done using a setting of equations and then deriving the transfer function, that could be done also. And that particular procedure is this one. The C over the error is equal to the G. Now, where did this particular thing came from? Now, I'd like to go back to this one, the B figure here. The C, the output, divided by the input, which is the error, will bring about the forward loop transfer function G. Okay? So, if the error is cross-multiplied to the G, then that would bring about this equation. C is equal to GE. The E coming from here, and it was just cross-multiplied here. This one came from the comparator. This came from, not from the comparator. This one came from the comparator. This is your set point, and what you subtract from it is the sense value coming from your measuring device or your sensing device. That's your error. This one is based on the reverse path. So I'd like to go back. In the reverse path, if you're going to look at this particular path in here, this one, that's your reverse path. Your output is B, your input is C, your transfer function is H. So, C times H is equal to B. C times H is equal to B. If you're going to work your way through these three equations, you will come up with an overall transfer function equivalent to this. So, this is the way you do it graphically. This is the way you do it using equations. And if you're going to ask me, it's better that you know how to derive the transfer function using the set equations, because it's not most of the time that you will have this particular type of block diagram in which it is easy for you to draw the simplified form, and then from the simplified form simplify it further to bring about the transfer function. Okay? So, it's better that you know how to do it using the setting up of equations. Now, this one is the overall transfer function still of your system relating C to R. What about relating C to U? This time, R is going to be set to 0, or there won't be any changes in the set point. It's only the load, or it's only your input variables that are experiences changing. Or shall we say they are your disturbances. Now, if you notice from our original block diagram, now the R was set to 0. So if this R is going to set to 0, nothing in this part of the branch is going to be affected because anyway, your R was set to 0. So it's like now you're going to cut this part. So what is remaining is only this part here. So the one that you're seeing is U, the input, and then your forward path in this case is G sub 2. This is your output, and this is your forward path times H. Your G2, your H, and your GC and G1. Now, there's something that I'd like to really emphasize here. Although we have cut this part of the system, because nothing goes inside here in terms of changes of the set point, nothing is being received by these particular blocks or transfer functions, you could see that still the denominator consists of the sum of 1 and the open loop transfer function. So you still need to multiply all the transfer functions in your block diagram to come up with a denominator that is still 1 plus GH. What changed here is the transfer function that appears in the forward path, primarily because the previous transfer functions, this G sub C and G sub 1, were taken out of the picture because we don't have an R. So if your block diagram, this one, was simplified in this form, it's so easy to write the transfer function. So it's C over U being equal to G sub 2 over 1 plus GH. Again, this is how you do it graphically. But if you're going to set up equations, this will be your equations. So in the first equation, you have C. Actually, this U over M is the denominator here. And you have the G sub 2. Now, let's check which part of the process this came from. So C over U plus M. So your C is here. And you could see in this summing junction that you have two input variables in this leg. So I'd like to first erase this one. Okay. Now, you could see that your C here, I'm going to cut through here. Your C is your output. Your input comprises of the sum of the U and the M because the sum of these two is the one that is being inputted or introduced to the G sub 2. That's the reason why you have this transfer function. So C over U plus M is equal to G sub 2. Okay, as 2M being equal to G sub C, G sub 1, and E, let's see. So it's just like you have M here over the error being equal to the product of G sub C and G sub 1. So let's go back here, and I'd like to erase this one. You could see that there are two transfer functions there that were being multiplied, and that's in the case G sub C and G sub 1. So it was actually cut in here. It was a cut in here. So your output is M, your input is the error working on the product of these two transfer functions. So you have M over the error is equal to G sub C, G sub 1, or error times G sub C times G sub 1 is equal to the M. That's the M that you have here. While this one is similar to the first transfer function derivation. B over C is equal to H. Where is that? Your B over C is equal to H, or C times H is equal to B. Or C times H is equal to B. Now this one is interesting. The error is just negative B. Why? The error is just negative B because, we'll erase this. Supposed to be, what you'll have is this. What you'll be having should be this one, the comparator. So the error should be equal to R minus B. But since R is 0, so the error is just equal to negative B. So that's the reason that you have this. If you're going to work your way through the four equations here, that would lead to the transfer function of our system that you are seeing here. The transfer function that relates the output to changes in the input variables, which are your load when there aren't any changes in the set point. Okay, that's how we derive the transfer function of C being related to U, because R here was set to 0. Okay, so this is your assignment which I gave you, and actually it was already posted in Canvas on where you're going to submit such an assignment. So the primary goal of this particular set of slides is to derive the transfer function of any system based on the block diagram. So either you do it using graphical technique or you do it using setting up of equations. I suggest that you should learn both. But I suggest that you should rely more on setting up of equations, because it's not always, as I've said, that your, shall we say, block diagram will be simple as what is presented here. So sometimes if it's complex, it will also be getting complicated as to how you're going to simplify such particular diagram. So thank you for listening, class.